In the next few videos, we'll be discussing a technique known as sliding window. This is a fairly common technique and you'll be coming across it in all sorts of problems. In this technique, we try to maintain a window that satisfies some given constraints. When the constraints are unsatisfied, we change the length of the window by increasing or decreasing the size. Even though the technique itself is quite simple in theory, its application could be quite challenging. We'll begin by solving fairly simple problems, applying the technique first, getting the intuition behind the technique, and then we'll move on to more advanced problems where using the technique might not be very obvious. Let's formalize what a window means. Here is an array of integers. A window is nothing but a group of contiguous array elements between two indices. In this diagram, a window could be this. Let's call this index rear and this one front. The window length here is 3. Now expanding the window could mean moving the front pointer forward while keeping the rear pointer fixed. Window length here becomes 4. Shrinking the window could mean moving the rear pointer forward while keeping the front pointer fixed. Window length here again becomes 3. If we move both pointers, rear and front, by the same distance, we essentially maintain the window length constant. As you can see here, window length is 3. Here is a rather simple problem to begin with. Given an array of size n, find the maximum subarray sum of length k. Now, just for the refresher on the difference between subarray and subsequence, a subarray has to be contiguous, while a subsequence does not have to be. Now, back to the question. Here is an array of integers with n, the array length, equal to 7 and k equal to 3. Out of all the possible subarrays in this array, we are supposed to find the one with subarray length equal to k equal to 3 and also having maximum possible sum. Now, just by looking at it, we can see the subarray with elements 3, 4, and 5 is the subarray with maximum possible sum with length equal to 3. Let's see how we can come up with the solution programmatically. We'll begin by looking at the brute force solution. Now, the brute force solution is very obvious. We iterate through each of the element, find the sum of subarray starting at that element and of length k equal to 3, compare it with previous max found, and repeat the process. Let's see it in action. We have two variables here, current window sum, the sum of the current window, and maximum window sum, which stores the max value of window sum found till now. We start with both of them being 0. We begin with the first element, that is 1, and find the sum of subarray of length 3 starting at this element. So we just traverse the next k minus 1 elements, adding the element while traversing. Here the subarray is 1, 3, and 4. The current window sum becomes 8 and max window sum is also 8. Now we do the same thing starting at the second element, that is 3 here. Current window sum becomes 12 and so does the maximum window sum since it is larger than the previous found value of 8. We move forward. Max window sum remains unchanged here since the current window sum is lesser than the previously found max. We repeat the process until we reach the end. We have our solution equal to 12 here. Let's quickly take a look at the code. We have a variable max window sum that we initialize with int min, the minimum possible value for an int, to help us with the first comparison. We've got two for loops. The outer one runs for I equal to 0 to n minus k, after which there are no subarrays of length k. Inside the loop, we have a local variable current window sum that keeps the track of the sum of current subarray in consideration. This runs beginning at j equal to I and goes forward till the given length of subarray k, that is till I plus k. Then we assign max window sum with the max of current window sum and the max window sum found so far. Finally, we return max window sum, which is our solution here. Time complexity of the solution here will be order of n multiplied by k, or order of n minus k into k to be more precise. So the inner loop is running for k times and the outer loop is running for n minus k times. So our time complexity here is order of n minus k times k. Now let's take a look at how we solve this in an optimized way. This is the same array we had previously. Before, we were calculating sum of each window starting afresh every time. We don't really need to do that. There's a lot of repeated work. The only thing that changes when we move from the first window to second is the element at the end. The element in between remains the same. If we remove the element 1 from window 1 and add the element 5 to it, we get this new window 2. So the idea is to maintain two pointers called rear and front. Both of them begin from index 0. We also keep two variables called current window sum, which basically keeps a track of sum of the current window under consideration. Max window sum keeps a track of overall max of all windows seen so far. Current window sum is 1 here, as we only have one element with value 1 in our window, and max window sum is 0 since we don't yet satisfy the constraint of window length k equal to 3. We expand the window by moving our front pointer forward, which now is at index 1. Current window sum becomes 4 here. We expand the window again, moving front pointer to index 2. This is the first window that satisfies our window length constraint of k equal to 3. So we update max window sum with value 8. If we expand the window again, the current window sum becomes 13, but we no longer satisfy the window length constraint. So we remove the element at rear from current window sum and we shrink the window by moving rear pointer forward. The constraints are satisfied again, so we update max window sum to 12 since 12 is greater than our previous max till now, which was 8. We repeat the process, add the element at front, remove the element at rear, update rear, compare with the previous max. Finally, we stop when we can't move forward anymore. Let's quickly code this up. We have a bunch of things already here to help us out. This is the brute force code which we already discussed. In the sliding window solution, we don't have much yet. We'll be filling it out. Inside main, we have a few arrays of integers and a bunch of assertion statements that are used to test the values returned by our functions above. So if we try running this now, we'll see this fails at line 38, which is our assertion statement for sliding window solution. Let's begin by defining a few variables first. We initialize current window sum equal to 0, max window sum, which holds our final result, equal to int min. We also have pointers rear and front that will mark our start and end of our window. Both will be at 0 initially. We iterate through the array elements. We add the front element to our current window. When front becomes greater or equal to k, we remove the element at rear from our current window sum and increment rear. If the window length, that is front minus rear plus 1, is equal to k, we update our max window sum to be max of max window sum and the current window sum. Finally, we return max window sum, which is our result. Let's see if our test cases pass now. They do. As for the time complexity of this solution, we only have one loop here and we are iterating through each of the elements only once. So the time complexity here is order of n. That ends our first video in this series. Thanks for watching.